So we want to start, please. Alex, thank you. Guys, come on. So we're very happy to have Ahmed Laghribi on the decomposition of central simple algebras of exponent 2 under multi-quadratic extension.
Thank you very much for the presentation. At the first, I would like to thank the organizer for giving me this opportunity to give a talk in this very nice conference. So this work is a joint work with Dembabari, and so I will start. So I will take F a field. For the moment, there is no restriction on the characteristic. And the problem that I will discuss concern the notion of adapted decomposition to some multi-quadratic extensions. But before that, this talk is in the framework of this general problem, really. If you take a central simple algebra, donc, if you take a central simple F algebra or a division algebra, if you want, and K field extension. So, of course, we would like to understand the structure of the algebra when the Schur index reduces after extending scalars to K. Okay, so we know some answers to this problem. For example, when K is the function field of projective quadric, this is the index reduction theorem by Merkuriev. When K is the function field of 14th Brauer variety, I think the answer was given by Vandenberg and Schofield. And for example, when K, the trivial case is purely transcendental extension did nothing happen, etc. But we are interested to the special case when K is multi-quadratic extension. It means that K is a field and it is isomorphic to tensor product of some Ki's, where each Ki is a quadratic extension. Okay, and if we have such K, we associate what we call the separability degree. The separability degree, it is to the n when n is the number of the extensions Ki which are separable over F. Okay. And because we are talking about the notion of decomposability, so I fix a definition. If we take a central simple F algebra, we say that the algebra is decomposable if there exists two central simple F algebra, A1, A2, not isomorphic to F, of course, not trivial, such that A is isomorphic to product of these two algebra. And we say that the algebra is totally decomposable if really it is isomorphic to tensor product of quaternion algebra. Okay. And by talking of quaternion algebra, so the definition was given in the last talk by Ahmed, but I will repeat something on this point. So a quaternion F algebra is given as follows. So if we are in characteristic 2, so if we are in characteristic 2, so the algebra I denoted by a symbol alpha beta, okay. This is the algebra generated by two elements, I and j, such that pi is alpha, g square is beta, and gi, j minus 1 is I plus 1. And what is p? P is just the usual Arthur-Schreier map. P goes from F to F and send hx to x square minus x. Okay, so, and you know here I write the bracket on the left and the parenthesis on the right, differently than what Hoffman used in his talk. And in characteristic different from 2, of course, you know, this is the algebra symbol, and we denote by two parentheses. The algebra generated by two elements, I and j, such that I square is alpha, j square is beta, and G minus 1 is minus A. Okay. But in characteristic 2, we have something interesting. So our quaternion algebra contains two fields which are quadratic over F. One is inseparable and the other one is separable. Okay. And now I arrive to the definition, which is in the center of our talk. We take a central simple F algebra, and I take a multi-quadratic extension such that it is contained in our algebra. And we see that the algebra has an adapted decomposition with respect to K if our algebra can be written like this up to isomorphism. Product of quaternion algebra Q1 until Qm, products with another central simple algebra A prime, such that the important thing is each Qi is F quaternion algebra, of course, and contains Ki. Okay, so if this situation happens, we say that our algebra has an adapted decomposition to K. And of course, when we see this definition, we can add central simple F algebra and key a multi-quadratic extension of F such that K is contained in A. We would like to understand under which condition does A has an adapted decomposition with respect to. Of course, the problem is very general and sometimes is very hard really to study. And the first thing to study this problem, we have to take into account numerical invariants that we attach to our base field. This invariant is CD2F, what we call the cohomological two-dimension of F, and it is a really very important invariant. So we have really to take it to account. And the definition of this invariant is what you see. CD2F is the smallest integer such that for any integer n at least equal to CD2F and any finite extension, this cohomology group is trivial. And I can recall you what is this cohomology group. So here we have to take, we separate between characteristic 2 and characteristic different from 2. Okay. So this group is defined as follows. Suppose that we are in characteristic 2. So this is just the n+1 Kato cohomology group. And this group is defined as follows. It is omega nf mod the omega n minus 1f e omega nf. And omega nf is the n, the space of n differential forms. I mean the absolute differential forms. Okay. And D is the differential operator, and P is the Artin-Schreier operator, which is an extension of the usual Artin-Schreier map that you know. Okay. This is if the characteristic is 2. And when the characteristic is different from 2, we have just the usual n+1 Galois cohomology group that we use. Okay. So this is the cohomological two-dimension of F, and the cohomology group is this one. Okay. And of course, because later I will work mostly with quadratic forms, so I would like to tell this remark. So using the isomorphism to Kato and Voevodsky and the Arason-Pfister-Hauptsatz, which is valid in any characteristic, we have the following. If the cohomological two-dimension is at most n, then for any finite extension LF, we have this group is 0. So this is just the definition, of course, using the isomorphism by Kato and Boykowski. And what is this group? This group, because we are not necessarily in characteristic different from 2, it's going to be characteristic 2. So the definition is the following. So as was said in the talk by Ahmed, so we have WF. This is the Witt ring of regular symmetric bilinear forms, of course, of finite dimension. And inside this ring, we have the usual fundamental ideal, okay? And we have an action of WF over WQF. WQF is the Witt group of non-singular quadratic forms. And now this group is defined as follows. If you are in characteristic different 2, you take the nth power of IF, this is bilinear parts, and you multiply it by the Witt group. And if the characteristic is not 2, you have the usual power of the fundamental, there is no difference. Okay, and now let's see, because as I told you, we have to take really into account this homological 2-dimension. So suppose that the homological 2-dimension is bigger than 2. So in this case, we know some facts, and it is important for the sequel. So we know that we have examples of indecomposable central simple F algebra of exponent 2. So you know the famous example, first one is due to Ahmed, Rawan, Signor, if the characteristic is different from 2. And recently, if characteristic 2, Barry, Chapman, and myself, we constructed an example. Okay, so we have indecomposable algebra, exponent 2, central simple algebra. And even if central simple F algebra A is totally decomposable and contains a multi-quadratic extension K, it is not necessary. It doesn't imply immediately that the algebra has an adapted decomposition with respect to K. And we have an example. For example, we have an example in degree 8. And KF is a separable quadratic extension. That was done by Barry if characteristic different from 2, and by Barry Chapman in characteristic 2, and myself. Of course, we used recently an invariant that we attached to any biquaternion algebra, and this invariant detects the descent of the biquaternion algebra, and using this invariant constructed such example. Okay, so for the moment, we see that if the homological 2-dimension is bigger than 2, so the situation is not, it's not good really to treat the adapted decomposition. But if the homological 2-dimension is at most 2, here we have some, we are in a nice situation. We know that any central simple F algebra of exponent 2 is totally decomposable. This is a result of Mercurier in characteristic different from 2. And this result was extended by Barry and Chapman. Moreover, we have a nice correspondence that says the following. This is due also to Mercurier, this observation. If you take a central simple F algebra of degree to the n and exponent 2, then you can find some phi in I2QF of dimension 2n plus 2, such that the Clifford algebra of phi is F of this shape. This is very important. Moreover, we can connect the Schur index of the algebra and the Witt index of the form phi. Okay, and I have to see that phi in this case is unique up to isometry. So the connection is the following. The Schur index is to the L if and only if the dimension of the anisotropic part of phi is 2L plus 2. In particular, the algebra is division if and only if phi is anisotropic. Okay, so I have to see that we will work really in this situation when the homological two-dimension is at most 2. And we see that in this case, the study of the adapted decomposition reduces really to specific questions on quadratic forms. Okay. So, so from now on, I will suppose that F is of characteristic 2. So until the end. So the specific questions on quadratic forms that we will need first, we will need the notion of excellence. Okay. So let me recall again the definition. So you take LF field extension. Okay. We say that LF is excellent if for any F quadratic form phi. So we take phi, we extend it to L. Probably it could be to become isotropic. It is possible, but in any case, we extend phi to L. We take the anisotropic part, and this anisotropic part, which is an L form, it should be defined over F up to isometry, which means that you find some psi over F such that psi over L is isometric to this form. Okay. This is the notion of excellence. But for the adapted decomposition, we need something very special. We need what I will call the notion of M excellence. Probably the notion of M excellence exists in the literature for other things, but I don't remember. So for the moment, I fix the notion of M excellence. So we say that the extension LF is M excellent if it is excellent only for forms, or if it is excellent for forms in IMQF, which means the following. Once you take for each form phi that you take in IMQF, you can find some psi in IMQF such that you have this isometry. You extend phi to L, you take the anisotropic part, and you will get your psi after extending scalar to L. Okay, and we will be really interested to the notion of two excellence to study our problem of adapted decomposition. So by talking on excellence, I give you some examples that you know. So the excellence, the extension LF is excellent in the following cases. So some examples. So the trivial one, when the extension is purely transcendental, this is obvious. Or where the extension is quadratic, for example, this is also easy to prove. Or where the extension is of odd degree, this is the result of or consequence of result of Springer. But I talk also about conics. Hoffman talks about conics, so I include conics. So FL is the function field of a conic, okay? Then the excellence holds for non-singular conics, for bilinear and quadratic forms, both. But we have to take non-singular conics. So in characteristic note 2, it was done by Arason first, and after that by Rost. Rost found a very elementary proof. And in characteristic 2, I did it with Hoffman. Just we took the same arguments by Rost and we adapted to the proof. It is not difficult. And for singular conics and bilinear forms, we have also excellence. So the function field of singular conic is excellent for bilinear forms. This was proved recently by Mokija. And the function field of a singular conic is not excellent for quadratic forms. I mean non-singular quadratic. Okay, this is just information about this notion. So now for the rest, I will take the two notations. XF is the set of all excellent extensions of F. And XMF is the set of all M excellent extensions of F. Okay. And now I give you other examples more than what I said. So we have a theorem which will play a really crucial role in our results. So let LF be a field extension. Then we have the following. If the extension is multi-quadratic, purely inseparable, then L is excellent. This is a very important result that was proved by Hoffman in 2015. Okay. And of course, when we see this result, we can naturally ask the question, what about multi-quadratic extension of separability degree 2? So for the moment, we have just small answer, but important one. If L is mixed by quadratic extension, I mean mixed, L is F square root of A alpha, such that alpha square minus alpha is B in F. So you mix separable and inseparable. Then the extension is excellent. It was proved by Mokija last year. Okay. And of course, any excellent extension is too excellent. But in general, the set of excellent extension is strictly contained in two excellent extensions. We have examples. Okay. And because we are interested to the case of homological two-dimension Atmos 2. So in this case, our field that we consider satisfy this condition, I3QF is 0. So suppose that I3QF is 0 and L is biquadratic separable or multi-quadratic of separability degree 2, then the extension is 2 excellent. Okay. And when we see all these examples, we can point out, we can ask some questions. The first question is to give some examples of extensions which are 3 excellent. So I didn't think a lot on this problem, but I have no example. Okay. And more precisely, we would like to know if XF is included in X3F. We don't know. Okay. Why here the situation is difficult? Because when you study the 2 excellence, okay, you do the descent, and after that, you deal with the RF invariant. But for the 3 excellence, you have to deal with the RF invariant. It is okay, it is not difficult. But also you have to deal with the Clifford invariant. And the notion of excellence does no control on the Clifford invariant. So this is the difficulty. And when we see this example, we can ask a question. Is it true that any multi-quadratic extension of F of separability degree 2 is excellent? So I think for no idea for that. But we have the first step, which is due to Mokija. And we can ask a general question. Let L F be a field extension and M at least 1. Under which condition or under which conditions L is M excellent? So here I try to point out another problem related to question 3. But the problem that I would like to talk about is the converse problem of this question tree up to with equivalence, not up to isometry. And the problem is the following. You take LF field extension, and we would like to know if IMQL, the intersection with this image of this homomorphism, this is just the restriction of homomorphism. Is it true that this intersection is contains in this image? Which means that you take a form in IMQL, you suppose that your form comes from F up to with equivalence, and we would like to know if we can find some form coming from this group. Okay, I think that the answer to this problem is yes for a very large class of fields. Okay, and this problem is related to another one. So this is the comment that I add. So the answer to this problem is related to the behavior of the degree under the extension L. Which degree I'm talking? I mean the degree in the sense of the Knibush generic splitting theory. You know, when you take a quadratic form, you associate two numerical invariants, the height and the degree. And this problem, C, is related to the behavior of the degree, this invariant degree, under field extensions. And in fact, it is nothing but reduced to this kernel, okay, in the setting of Kato cohomology. So if you can answer this kernel for L, we can see something for this problem C. Okay, and now I will give you some answers that I will use later for the adapted decomposition. Okay, so we have a theorem due to Laghribi, Orion, and myself. So we proved it in 2 times, 2013 and 2020. So I take M, a multi-quadratic, purely inseparable extension. And I take M prime biquadratic separable extension. And this biquadratic is given like this. P of alpha I is Bi as you see. And now I take my field L1, it could be M or M alpha or M alpha 1, alpha 2. Okay. And now this kernel for each field of these three fields is given as follows. So if L is M, the kernel is what we expect. There is no surprise. Okay. If we add a separable slot, also the kernel is what we expect. But here we have, of course, new factor because we add separable slot. And the hard answer is the third one. When you add second separable slot, the kernel is what we expect. And this computation of this third kernel really is very hard because we used other result that was proved by Laghribi and Jacob. Some difficult result. Okay. And here you see this group. We have new FM. What is it? New FM is just the kernel of the Arthur-Schreier operator P. Okay. And FM is just the group additively generated by Delog's symbols. Okay. Good. And now we have to return to quadratic forms. So here we have the Kato isomorphism, the famous one, and that was defined by Ahmed. And here we have the cohomological symbols, and we have this correspondence. So using this isomorphism, we can compute this kernel. Obviously, there is nothing to do here. So just translate the description in the language of differential forms to the language of quadratic forms. But the important thing is to descend a level down, I mean, at the level of Witt group. And here we use a trick that we use usually to reduce to a field having a finite two bases. So, and we get the following corollary. So we keep the notations and hypothesis as in the previous theorem, and this kernel now, just the filtration of about the Witt group, there is no graduation, is equal to the following. If L is M, we get this kernel. And here you see that we respect the degree. Here you have degree M plus 1. Here you have degree M. And this has degree 1. So we are in degree M plus 1. And it is very strong. And if L is M alpha 1, we get the same thing as we expect. And so, okay. And what is this notation? 1E1, it is just the diagonal bilinear form, not the diagonal quadratic form, diagonal bilinear. And this form is just the two-dimensional regular quadratic form. Okay? And the corollary is that problem C has positive answer for quadratic extensions of separability degree at most 4. But I'm sure that there are other examples. I will give another example. Okay. So here, the hard part is to compute this cohomological curve. Use it to answer the problem C is not difficult. And I will give you the proof. It is very easy. Once you know the cohomological kernel, you can see something on problem C. So let's see, for example. So I restrict myself just to this extension, just to show you how it works. It is just we will increase the degree step by step until we reach IM. So we take L, purely inseparable multi-quadratic extension of exponent 1, and we have to prove this inclusion. Okay, so we take phi in this group, and we suppose that phi comes from WF up to Witt equivalence. Okay, so we have this. And now let's be, because the Witt group is has a filtration, okay, by the groups I, N, Q, F. So psi will be in some I, P, Q. Okay, we have two cases. So there is nothing to prove if M is less or equal to P, because we are done. Psi, this is the form that we are looking for. So this is not into. But the important part, or to complete the proof, is when P is smaller than M. Okay. So now, if you take this Witt equivalence, this condition implies that this class belongs to this kernel, the graded kernel. Okay, so now we apply the previous corollary, and we get this relation. And here you see, we started with psi in IP, and now we corrected our psi by this form, and the degree decreased by 1. Okay, and we continue. Now, instead of taking psi, you take all this new form. Okay, and we have clearly this double Witt equivalence, because the correction, it becomes 0, it becomes hyperbolic when you pass to L. So, and we repeat the argument now that we use for psi, we use it for psi prime, until we get a form gamma of this shape psi plus some correction, and we are in I, and we are done. So you see that once you compute the kernel, you can answer the problem C easily. This is not difficult. Okay. And a remark, problem C has a positive answer also. So if you would like to go beyond algebraic extension. So I choose this example. Our L is a compositum with M and FB, such that M is a multi-quadratic extension of separability degree at most 2, and B is a bilinear Pfister form. So for this field, problem C has also a positive answer. And here I see B a bilinear Pfister form. If you change B by bilinear Pfister form by a quadratic Pfister form, the problem is open. We don't know. Okay, and here I'm talking about B, bilinear form. What is the function field of bilinear form? If you have a bilinear form, you take B tilde, this quadratic form defined as follows. And FB by definition is the function field of this quadratic. Okay, so, and another result that I have, I would like to mention, but I will not use it directly in my proof, is the following. If you suppose that IMQF is 0, then IMQL is 0 for L multi-quadratic. We don't care about the separability degree. It is true all the time. Okay. And now back to adapted decomposition. What we know on this point. So adapted decomposition, in the sense of the definition that I gave before, is satisfied for quadratic and bi-quadratic extension, under the hypothesis that the cohomological two-dimension is at most 2, and of course the exponent is 2. So this was done by Barry in characteristic different from 2 and by Chapman in characteristic. And now I will give you some examples, something that we proved, and it goes really beyond quadratic or bi-quadratic extensions. So our contribution on this problem is the following. So suppose that the cohomological two-dimension of F is at most 2, okay? Let D be central division F algebra of exponent 2 and degree to the n. And let K be a multi-quadratic extension of degree to the K, such that K is one of the following types. So first, K could be, K has separability degree of at most 2, and the index of decay is to the n minus K, okay? Or K is of separability to the degree 4, and decay is split. Or K is 3 quadratic of separability degree 4, and I take n at least 4, and the index of decay is 2 to the n minus 3. Of course, these 3 cases excluded mutually. And if K is one of these 3 types, then D has an adapted decomposition with respect to K. Of course, here you see that we couldn't answer completely the case of separability degree 4. And where is the problem? The problem comes from the following. So the case of separability degree 4, suppose that K has separability degree 4. If question 2, Q2 that I pointed out before, if question Q2 has a positive answer, then the adapted decomposition holds also for K. So let me remind you what is Q2. Question Q2 is the following. This is one. Question Q2. We would like to say if multi-quadratic extension of separability degree 2 is excellent. Okay, So now I will give you an idea, really very simple idea, how to prove theorem 3. I will not treat all the 3 cases. I will restrict myself only for K, purely inseparable multi-quadratic extension. So sketch of proof, the previous theorem. So we restrict ourselves to K, which is the square root E1 square root A. And for the case of separability degree 2 or 4, we use statement 4 of theorem 1. And let me recall you the statement with, what is it? This one, so this statement, okay? This is the statement that we use. Okay. So suppose that the degree of D is to the n. Since the cohomological two-dimension is at most 2, we say that D is totally decomposable. Okay. And by the correspondence that I gave you, we can find a form phi in I2QF anisotropic of dimension 2n plus 2, such that we have this condition. The Clifford algebra of phi is isomorphic to M2D. Okay. Now, since the index of dk is 2 the n minus k, and the cohomological two-dimension of k is at most 2, we have this condition. The dimension of the anisotropic part of k is 2n minus k plus 2. And because k is too excellent, this form can be written like this, for some psi in I2QF of dimension 2n minus k plus 2. Okay, that is good. And we have to note the following. The Clifford algebra of psi is isomorphic to M2 and the product of n minus k quaternion algebra. Okay. So now this condition gives the following. It means that this form is hyperbolic, is clear. And now using the kernel that I showed a few minutes ago, phi plus psi can be written like this, where h phi I is in the Witt group. Okay. And now we pass to the Clifford algebra. We take the Clifford algebra in this step, and we get the Clifford algebra of phi is Brauer equivalent to the Clifford algebra of psi tensor product with this quaternion algebra. And here we have this I, we have it here. Okay. And BI is just a representative of the R invariant of phi. And now it is okay. We say that C phi before it is M2D. So we write it and we get this Brauer equivalence. And now if we compare dimensions, we get really this isomorphism. And here we see our factors EI that compose the field K. So it is simple, it is not there. For separability degree 2 and 4, we have to be careful on some points, but it is more or less the same. Okay. Now, what about separability degree 8? So unfortunately, the adapted decomposition is no longer true for multi-quadratic extension of separability degree 8. And we produced an example, and the example is here is theorem 4. It says the following. There exists a field F of characteristic 2 such that the cohomological two-dimension of F is 2. There exists a separable triquadratic extension KF, central simple algebra A of degree 8, exponent 2, and index 2. such that AK is split, but A has no adapted decomposition with respect to K. Okay, so this is the example that we produced. So these examples took us a lot of time, so it was not really easy to find this example. And of course, to deal with multi-quadratic extensions of separability degree for 3 quadratic separable extensions. And in the literature, we have an important paper due to of Lieb and Smith. This is a paper in characteristic difference from 2, and in the reference is this. Okay. And in this paper, the author studied the width kernel of 3 quadratic extensions in characteristic node 2. And of course, this case is very hard. They couldn't complete this case, this kernel, but they gave very important informations. And one of the results that we used from their paper is the following proposition. I give you just a proposition and I will comment a little bit. So the analog of this proposition is in their paper, but we adapt it to our case. You take M, separable 3 quadratic extension, and you take K is F alpha 1. And over K, you consider this form. So here you have B2, it is related to alpha 2, B3 is related to alpha 3. And beta is like this, gamma is like this. There are scalars in K. And this form, the proposition says that this form is defined over F if and only if we have this isometry that you see between twofold quadratic filter. Okay, what is the importance of this proposition? So before that, let me note something. So if you see this form phi, when you extend it to the M, it becomes hyperbolic. Because when you extend to M, you will kill B2 and B3. Okay. And the importance of this proposition, this is what I wrote, is the following. You can, this proposition gives you an idea to construct a form over a separable quadratic extension that becomes hyperbolic over 3 quadratic separable extension. And if you are lucky, this form can be defined over F. And this is what we used. Okay, so now idea of the proof of theorem 4. Let me recall you that theorem 4 is this example. So we take K, an algebraic closed field, F of characteristic 2, and we take F is K, X, Y, the field of fraction in the 2 variables, X and Y. And we construct the 3 quadratic separable extension as follows. We take M is F alpha 1, alpha 2, alpha 3. Okay. And such that P alpha 1 is X. And this element, for some reasons, I will call it A, just to. And P alpha 2 is this element that you see, and I will call it B. And P alpha 3 is this element with variables that I will call it C. It is not difficult to prove that this extension is really of degree 8 over F. And taking inspiration from proposition that I gave you 1 minute before, we put this form over this field, we consider this form. You see here, my beta and my C, I put them here, as in the proposition. This is my beta, and this is my gamma, as in the proposition. And this form meets all the conditions in the proposition. It is defined over F. Okay, so there exists psi in WQF such that we have this isometry. If you would like to ignore the proposition, the previous one, you can prove that phi is defined over F using some the following arguments. For example, you take the Charlow transfer S star induced by the F linear map S from F alpha 1 to F, that's send 1 to 0 and alpha 1 to 1, and you prove that the transfer of phi is 0, which means that phi is defined over F up to bit equivalence. And because the extension F alpha 1 is excellent over F, we conclude that phi is defined over up to isometry. Okay, this is the first point. The second point, psi over M is hyperbolic. And the reason is the following. If you remember, so B and C are P of something. Okay, so they are in PM. So my form becomes hyperbolic over M, and the same thing is true for psi. So my psi now is in the Witt kernel of M. But the crucial step is that this psi, it is the Witt kernel of M, but it is not in the part that we expect. This part, it is included in the Witt kernel, but psi, it is not there. Okay, so how we prove this? We will work over another field, this one. And over this field, we have this form. Here, this is bilinear form of dimension 2 and a regular quadratic form of dimension 2. So this is a twofold Pfister form. That becomes hyperbolic over A. And now we translate in the language of catohomology. It means that this cohomological symbol is 0 in H2 to E. And this is the two torsion of the Brauer. Okay? What is zeta? Zeta is this element. So this element, I call it zeta. Okay? And what does mean this what does mean this cohomological symbol is 0? It means that this element is in the annihilator of this D-log. Annihilator in the sense of what? In the sense of this action, exterior action. Okay, and this annihilator, we know it thanks to a result of Araveri and Baeza. So this class, we can write it zeta A square, where A is this field. Working a little bit, we can prove that A is in F. Okay, and now all is okay. This equality, it is over A, which means that you have this isometry over our base field F. And working with some residues form, we prove that this isometry is not possible. Okay, so now the final step, we take theta like psi 1 delta psi as the hyperbolic plane. Okay, so theta is in I2QF. The Clifford algebra of theta is M2A, where A is the algebra for which we are looking for. It is of degree 8 and index 2. Because psi is hyperbolic over M, theta is also hyperbolic and the algebra is split. But the algebra has no adapted decomposition because of the previous claim. Okay, so this is about the construction. Now the excellence, our method allows us something more. The extension F alpha 1 alpha 2 is not excellent. This is another example of non-excellence of biquadratic separable extension. So I skip the proof, it is not important. And now let me tell you a few words what we know about excellence or no excellence for quartic extensions. The no-excellence of biquadratic extensions, the first example in characteristic note 2 was given by Ehlmann, Lam, Tignol, and Wadsworth. Few years later, Sivatsky gives another example that used the existence of undecomposable algebra of degree 8 and exponent. And recently, Mokija extended these Sivatsky examples to characteristic. But what about other separable quartic extension? We don't know. There is nothing. Okay. But for quartic inseparable extension, the picture is complete, really. If you take a quartic inseparable extension, it is one of the following types. We have 4 types. We have biquadratic purely inseparable. We have mixed biquadratic. We have simple purely inseparable, and we have simple not purely inseparable. So for biquadratic and mixed, we have all the time excellence. This is what I said. This is Hoffman and Mokij. And for the other 2 types, simple purely inseparable, quartic of course, or simple but not purely inseparable, we have no excellence. Okay, and now the last thing. In contrast of theorem 4, what is theorem 4? Let me recall you theorem 4. This is this theorem. So you see here, we have index 2. And we can ask, what about index 4 and 8? Is it possible to construct counterexample or example? And how? So for index 4, I don't know. It seems to me that we can construct example. But for degree 8, we are in a rigid situation. So probably the answer is yes. So the question is the following. Let D be a central division of algebra of degree 8, exponent 2, cohomological 2 dimension is 2, and let M be a separable 3-quadratic extension such that dk is split. Is it true that D has an unadapted decomposition with respect to K? So we have no answer. And for sure, to try to answer this question, the first step is to try to understand the bit kernel of 3-quadratic separable extension. So if you take separable extension like this, okay, with this condition, the bit kernel is decomposed like this. We have the part that we expect, and we have the obscure part we don't know here. Lipp and Smith, in characteristic difference from 2, gave information on A. But I think the right way to get information on this part A is to start the study at the level of Kato cohomology. So to get more information on A, it is better to study the kernel of the Kato cohomology. And this kernel also is the parts that we expect plus this part. But for Kato cohomology, we have more tools. We can do something in flexible way than bit group. Thank you very much. This is all.
Question? Let's thank the speaker again.
Thank you very much.